Variable selection is a crucial procedure in high-dimensional data analysis, aiming to identify the most informative predictors for a response variable. However, complex nonlinear dependencies and strong coupling between variables pose significant challenges to existing methods. To address these challenges, this paper proposes a transparent and nonlinear variable selection approach. The method employs a three-step heuristic search to group input predictors into four subsets: relevant predictors to be selected, and uninformative, redundant, and conditionally independent predictors to be removed. A nonlinear partial correlation coefficient is introduced to identify predictors with nonlinear functional dependence on the response variable. The proposed method is model-free, meaning it does not rely on a specific predictive model, and the selected subset of predictors can serve as input for various commonly used predictive models. Experimental results demonstrate the superior performance of the proposed method compared to state-of-the-art baselines in terms of prediction accuracy and model interpretability. The current section delves into the limitations of traditional variable selection methods, which often assume linear or monotonic relationships between predictors and the response. These approaches struggle with nonlinear dependencies, interactions among predictors, and the presence of uninformative and collinear predictors. To address these challenges, the authors introduce the transparent and nonlinear variable selection (TNVS) method. TNVS categorizes predictors into four subsets based on nonlinear partial correlation, information entropy, Gram-Schmidt orthogonalization, and nonlinear partial correlation coefficients. This approach aims to identify predictors with complex nonlinear relevance and eliminate uninformative, redundant, and conditionally independent predictors. The effectiveness and interpretability of TNVS are demonstrated through simulations and real data applications, showcasing enhanced predictive accuracy and model transparency. In high-dimensional data analysis, traditional feature screening methods based on partial correlations often struggle to capture all relevant predictors, particularly when complex interactions exist among predictors. Stepwise methods, such as PC-simple and TPC, can be employed when prior knowledge of key variables is limited, but they are restricted to linear regression models and fail to identify nonlinear conditional relevance between the response and predictors. Recently, the conditional dependence coefficient, codec, was developed to measure nonlinear conditional dependence between two variables given a set of other variables. Building upon codec, the feature ordering by conditional independence (foci) method was proposed to identify conditionally dependent predictors from complicated associations. However, foci is computationally intensive and challenging to interpret. To address these limitations, a novel transparent information decoupling approach is introduced, which categorizes the input set of predictors into four disjoint subsets: relevant, redundant, uninformative, and irrelevant predictors. This approach enables the elimination of uninformative and redundant predictors, allowing for the selection of non-monotonic nonlinear relevance. Existing methods, including SIS, SIRS, DCSIS, WLS, PC-simple, TPC, and foci, are limited in their ability to provide transparent and interpretable variable selection. The proposed method, TNVS, is designed to overcome these limitations, offering a more effective and interpretable scheme for variable selection. By providing a transparent information decoupling approach, TNVS addresses the need for a fully interpretable method that can selectively remove certain types of predictors. The concept of information decoupling involves dividing input predictors into four disjoint subsets: relevant, uninformative, redundant, and conditionally independent. The relevant subset, denoted by S, comprises the indices of the true model, which can be expressed as y equals f, xs, plus epsilon, where epsilon is a stochastic error. The primary goal is to identify the correlated subset S from the input set X using the conditional dependence coefficient, codec. Codec measures the nonlinear conditional correlation between Y and a predictor Xj given a set of predictors Xg, calculated using equations 1 and 2. It converges to a limit in 0, 1, indicating conditional independence, 0, or almost sure equality, 1. Codec can also measure unconditional correlation by setting G equals empty set and using equation 2. The novel variable selection method, codec, leverages conditional entropy to identify relevant predictors in high-dimensional data. This approach is based on the principle that the response variable y should exhibit high conditional entropy given the predictor set xg, but low conditional entropy given the predictor set xj, indicating that xj does not contain additional information about y beyond what is already present in xg. Codec is applicable to both continuous and discrete predictors. For discrete predictors, Shannon entropy is used to measure their information content. Continuous predictors, however, require data discretization before applying Shannon entropy. The method also introduces the concepts of uninformative and redundant predictors. Uninformative predictors are characterized by zero Shannon entropy, signifying that they contain no information about the response variable. Redundant predictors are identified using Gram-Schmidt orthogonalization, which decomposes the predictor set and measures multicollinearity among predictors. If the variance of an orthogonal variable zj equals 0, it indicates that all the information of xj is already contained in xg, making xj a redundant predictor. By first removing uninformative and redundant predictors, the codec approach aims to improve the efficiency of variable selection, which can significantly enhance the performance of machine learning models. In high-dimensional data analysis, identifying conditionally independent predictors is crucial to maintain interpretability and prediction accuracy. Conditionally independent predictors, if not properly handled, can compromise model performance. The codec measure is employed to quantify the degree of conditional independence among predictors. To address this challenge, the transparent and nonlinear variable selection (TNVS) approach is proposed. This three-step heuristic search methodology separates candidate predictors into two distinct categories: those to be selected and those to be deleted. The TNVS approach is visually illustrated in Figure 2, which outlines the stepwise process for identifying uninformative, redundant, and conditionally independent subsets. The TNVS approach begins by identifying uninformative predictors, which do not contribute to the target response. Next, it detects redundant predictors that are highly correlated with other predictors. Finally, the approach identifies conditionally independent predictors that do not provide additional information given the relevant subset. By systematically eliminating these predictors, the TNVS approach enhances model transparency and accuracy. The TNVS heuristic search involves three steps: prefiltering, forward selection, and batch deletion. In the prefiltering step, uninformative predictors are identified and removed based on their uninformative score. Forward selection involves identifying the most relevant predictor to the response given the current subset of selected predictors. The batch deletion step removes redundant predictors that are collinear with the selected predictors. The algorithm terminates when the relevant subset reaches a predetermined size or when no more relevant predictors can be found. This efficient selection process aims to reduce dimensionality while preserving relevant information. The authors propose a novel variable selection method, TNVS, which divides the index set of predictors into four mutually disjoint subsets: relevant, uninformative, redundant, and conditionally independent predictors. This method consists of three steps: prefiltering, forward selection, and batch deletion. The computational time of TNVS is O(dn) ln, making it efficient even with limited processors. The main advantages of TNVS are its transparent framework, ability to handle high-dimensional data with complex nonlinear associations, and model-free nature. The selected subset of predictors has strong generality and can be used to construct various learning models. The authors conduct simulation studies to evaluate the effectiveness and interpretability of TNVs. They generate a regression simulation problem with 90% informative predictors and 10% uninformative predictors, featuring nonlinear measurable functions of some predictors, interactions, multicollinearity, and conditionally independent predictors. The simulation settings vary in terms of the number of samples, n, and predictors, p, with three settings: n equals 2000, p equals 1000, n equals 2000, p equals 2000, and n equals 2000, p equals 5000. For each setting, 10 datasets are generated to evaluate the performance of TNVs. The response variable is defined as y equals 2xt1 xt2 plus cos pi xt3 xt4 plus epsilon, where epsilon is the stochastic error following the normal distribution. This function represents a nonlinear correlation between the response and predictors, with oscillatory functional dependence on xt3 and xt4, and interactions between xt1 and xt2, and xt3 and xt4. The experimental setup for evaluating the effectiveness and efficiency of the proposed method, TNVS, involves high-dimensional simulations with complex nonlinear functional dependencies. 6 baseline models are used for comparison, with evaluation criteria including the probability of discovery of all truly important predictors, PA, minimum model size required to include all true predictors, M, coverage, and computational time. The results, summarized in Table 2, demonstrate TNVS's superior performance compared to traditional methods and its ranking as the most effective and efficient among the 3 novel methods, foci and WLS. Notably, TNVS requires a smaller minimum model size and exhibits a larger coverage than foci, indicating its accuracy and reliability. Furthermore, TNVS achieves the least computational time among the 3 methods, showcasing its efficiency. The parameter settings for each variable selection method and the computational environment used for the experiments are also provided. These details enable a comprehensive understanding of the experimental design and facilitate the replication of results. By outperforming existing methods, TNVS establishes itself as a promising approach for variable selection in high-dimensional datasets with complex nonlinear relationships. The authors evaluate the performance of their proposed method, TNVS, against 6 prevailing methods: foci, WLS, SIRS, DCSIS, PC simple, and TPC across 3 nonlinear simulation settings. The assessment is based on 4 key performance metrics: PA, M, coverage, and running time. The results, as presented in Table 2, demonstrate the superiority of TNVS, achieving the highest PA values, indicative of its ability to accurately identify true predictors while minimizing false positives. Notably, TNVS also exhibits higher coverage and significantly lower running times compared to the other methods. In contrast, methods such as SIRS, DCSIS, PC simple, and TPC struggle to identify nonlinearly relevant predictors, omitting true predictors and including irrelevant ones. Foci, which also employs the nonlinear codec, fails to remove uninformative and redundant predictors, resulting in lower performance. To further investigate the interpretability of TNVS, the authors analyzed the proportions of truly relevant, uninformative, redundant, and conditionally independent predictors in the selected subsets of TNVS, foci, and WLS. The results, shown in Table 3, reveal that TNVS selects the largest proportion of truly relevant predictors and the smallest proportions of uninformative, redundant, and conditionally independent predictors, demonstrating its ability to identify concise and accurate subsets of predictors. Overall, the authors demonstrate the effectiveness and efficiency of TNVS in identifying nonlinearly relevant predictors, achieving high precision and low false positive rates, and outperforming existing methods in nonlinear simulation settings. The comparison in Table 3 shows that TNVS enhances the capability of foci to handle the lack of information and multicollinearity, achieving a better balance between accuracy and conciseness than WLS. Specifically, TNVS effectively identifies and separates relevant predictors, uninformative predictors, redundant predictors, and conditionally independent predictors. Table 4 summarizes the proportions of ground truth types of predictors in the 4 subsets obtained by TNVS, including the relevant subset, uninformative subset, redundant subset, and conditionally independent subset. The average of each quantity in all 100 repetitions is provided. The truly relevant predictors grouped into the selected relevant subset are true positives, whereas those grouped into the other 3 types are false negatives. The diagonal elements of Table 4 represent the recall of TNVS, demonstrating its unique strength in not only selecting relevant predictors but also dividing predictors to be removed into 3 distinct subsets. The results suggest that TNVS is an effective method for variable selection, capable of handling complex data structures and providing insights into the relationships between predictors. The TNVS method demonstrates superior model interpretability performance compared to baselines. To evaluate its effectiveness, 4 real-world datasets from diverse domains are utilized: ArXiv for mass spectrometry, Isolet for audio, Warpart 10P and ORL for facial recognition. These datasets are chosen for their high dimensionality, nonlinear correlations, and numerous redundant predictors, making them ideal for assessing the method's capabilities. The face image datasets, in particular, facilitate visualization of variable selection results. Each dataset is meticulously described, highlighting its unique characteristics and the rationale behind its selection. To ensure consistency, all predictors are normalized using z-score normalization, which enables meaningful comparisons across datasets. The proposed TNVS model is evaluated for its effectiveness and generality by comparing it to 5 prevailing predictive models: SVR, SVM, RF, DT, Light GBM, and MLP. Each learning model is trained with the selected predictors, and the results are compared to demonstrate the superior generality of variable selection methods. The configurations of the learning models are set to be identical to avoid favoring any individual method. The evaluation uses out-of-sample accuracy, recall, F1, and Cohen-Kappa score. The results, as shown in Fig. 3 and detailed in Table B1, demonstrate that TNVS is robustly superior to the baselines. A statistical test, such as the Friedman test, is performed to further support these findings. The Friedman test is employed to evaluate the overall performance of the proposed variable selection method, TNVS, in comparison to 6 other methods on real datasets. The results, presented in Table 6, demonstrate that TNVS attains the top 2 ranks among the 7 methods, with significant differences among the methods. This confirms the strength and robustness of TNVS in prediction enhancement. The Friedman test provides a mean rank of the methods, with a higher mean rank indicating better performance. The p-value of the Friedman test indicates the significance of the differences among the methods. As shown in Table 6, the mean rank of TNVS is higher than the other methods, and the p-value is close to 0, indicating significant differences. Furthermore, the interpretability of TNVS on real datasets is evaluated. TNVS transparently groups the predictors into 4 subsets: relevant, uninformative, redundant, and conditionally independent. The average cardinalities of these subsets are counted, and the average compression rate is calculated, defined as the proportion of relevant predictors in the inputs. The results, presented in Table 7, show that the percentage of relevant predictors is lower than 6% in all datasets, indicating that TNVS compresses the input set of predictors to a large degree. Redundant predictors are identified in all datasets, demonstrating the usefulness of the group sparsity optimization (GSO) component. Additionally, the variable selection results of the ORL dataset are visualized to demonstrate post-hoc interpretability of TNVs. The selected pixels are marked on the original images, with relevant pixels colored in yellow, redundant pixels in red, and conditionally independent pixels unmarked. This visualization provides insight into the key predictors of the observations, capturing the key reference points on the face that could help identify an individual, such as the annotated facial landmarks in the wild. AFLW marked 21 facial feature points. The proposed method, TNVS, demonstrates superior performance in selecting relevant pixels for facial recognition tasks using the ORL dataset. Comparative analysis with baseline methods, including foci, WLS, SIRS, DCSIS, PC Simple, and TPC, reveals that TNVS achieves comparable or better predictive performance while maintaining a more concise subset of predictors. Visualization of the selected and removed pixels by TNVS, as shown in Figure 4, illustrates its ability to accurately detect key reference points in the faces, including eye corners, eyebrow corners, tips of the nose, corners of mouth, and chins. This explains the superior facial discrimination achieved by TNVS and WLS, which are the top 2 performing methods on the ORL dataset. In contrast, foci selects fewer pixels than TNVS but omits redundant pixels, while SIRS and DCSIS select a large number of redundant pixels in the forehead, omitting some feature points in the eye corners, eyebrow corners, and tips of the nose. PC Simple and TPC, on the other hand, omit many important facial feature points. The robustness of TNVS against variations in the three thresholds used in the method is also explored. By tuning these thresholds within certain ranges, it is demonstrated that the outperformance of TNVS is persistently significant, and the method is robust against hyperparameter variations. This is a crucial aspect, as real-world data often contains noise, and a robust method should be able to handle such variations effectively. Overall, TNVS demonstrates its effectiveness in identifying relevant and redundant pixels for facial recognition tasks, its robustness in tuning parameters, and its superior performance compared to baseline methods. In high-dimensional data analysis, the transparent and nonlinear variable selection (TNVS) method offers a novel approach to selecting relevant predictors while eliminating uninformative, collinear, and conditionally independent variables. This three-step heuristic search process involves identifying complex nonlinear functional dependencies through a nonlinear partial correlation. To assess the stability of TNVS, the authors perform a 10-fold cross-validation on 4 real datasets, varying key parameters to test its robustness. The results demonstrate that TNVS is insensitive to threshold changes within specific ranges, ensuring reliable variable selection. The TNVS method's nonlinear partial correlation is a key innovation, allowing it to capture intricate relationships between variables that traditional methods may miss. By iteratively refining the set of predictors, TNVS provides a transparent and efficient means of identifying the most informative variables in high-dimensional data. This approach is particularly valuable in domains where data dimensionality poses significant challenges, such as genomics, finance, and climate modeling. The author's thorough evaluation of TNVS using real-world datasets and varying parameters underscores the method's versatility and reliability. By providing a robust and interpretable framework for variable selection, TNVS has the potential to significantly enhance the accuracy and reliability of high-dimensional data analysis. TNVS, a novel method for variable selection, identifies relevant predictors and eliminates unimportant ones in regression models. It employs a 3-step heuristic search that considers non-monotonic or oscillatory functional dependencies and interactions among predictors. This approach enhances model interpretability through a clear selecting and deleting process. The method's effectiveness is demonstrated in its ability to handle complex relationships among predictors. However, limitations exist. For instance, empirical thresholds used in the 3-step heuristic search can be improved using non-parametric statistical tests. Additionally, TNVS struggles to identify marginal independent but jointly correlated predictors, where domain knowledge can provide better support. Future improvements include incorporating genetic algorithms or other metaheuristic algorithms to enhance efficiency in high-dimensional scenarios with less sparse data. The method's capabilities are showcased in the appendix, where an example demonstrates its ability to identify relevant, uninformative, multicollinear, and conditionally independent predictors. This research was supported by grants from the National Natural Science Foundation of China, with no competing financial interests or personal relationships influencing the work. The histogram of X6 is discussed, highlighting its uninformative nature, and the dependencies between Y and X2 or X5 given X1 are considered. The proposed variable selection method involves prefiltering, forward selection, and batch deletion steps. It aims to identify uninformative predictors, select relevant predictors, and remove redundant predictors. The search stops when no more predictors can be added or removed based on the rels values. The method's performance in real datasets is then presented, including the mean and standard deviation of models such as TNVS, foci, WLS, SIRS, DCSIS, PC Simple, and TPC. The results are compared, with the best results highlighted in bold and the second best results underlined, providing a comprehensive overview of the variable selection method and its performance. The comparative analysis of machine learning models, including light GBM, MLP, SVM, and random forest (RF), demonstrates varying levels of accuracy, recall, F1 score, and kappa values across different datasets. Light GBM shows a high accuracy of 0.6841 with a standard deviation of 0.1156, indicating consistent performance. Its recall and F1 score are competitive, at 0.7249 and 0.7197, respectively, with similar variability. The kappa value of 0.3808 suggests moderate agreement between the model's predictions and actual outcomes. MLP exhibits slightly lower accuracy and recall, at 0.8113 and 0.8813, respectively, but maintains a comparable F1 score of 0.8791. The kappa value for MLP is 0.8576, indicating substantial agreement. SVM displays a lower accuracy of 0.7015, along with a recall of 0.7015 and an F1 score of 0.8076. Its kappa value is 0.7736, reflecting fair agreement. Random forest, RF, shows a balanced performance across all metrics, with an accuracy of 0.8807, recall of 0.8807, F1 score of 0.8791, and a kappa value of 0.8576, demonstrating strong agreement. The results emphasize the importance of selecting the appropriate model based on the specific dataset and task at hand. This section of the paper presents a comprehensive analysis of various machine learning models' performance metrics, including F1 scores, kappa statistics, and recall values. The models evaluated include RF-ACC, SVM-ACC, MLP-ACC, and Light GBM-ACC, among others. The results show a range of performances, with RF-ACC and MLP-ACC demonstrating higher F1 scores and kappa statistics, indicating better accuracy and consistency in their predictions. The recall values also vary, suggesting differences in each model's ability to detect all relevant instances within the dataset. This data is crucial for understanding the strengths and weaknesses of each model in real-world applications, aiding researchers and practitioners in selecting the most appropriate model for their specific needs. The experiments evaluate the performance of various machine learning models on different datasets using selected predictors under different parameter settings of TNVs. Models considered include support vector machine, SVM, random forest, RF, decision tree, DT, Light GBM, and multilayer perceptron, MLP. The tables display the F1 score, kappa coefficient, MLP accuracy, and recall for each model on the RScene, Isolet, Warpart 10P, and ORL datasets, along with their corresponding standard deviations. The figure, C1, visualizes the accuracy of different learning models using the selected predictors under different parameter settings of TNVS, with the z-axis representing the different models and the y-axis representing the accuracy. Feature selection is a crucial step in high-dimensional data analysis, as it enables the identification of relevant variables that underlie complex phenomena. The importance of feature selection lies in its ability to reduce dimensionality, eliminate noisy or irrelevant features, and improve model interpretability. Several techniques have been developed to address the challenges of feature selection in high-dimensional data. Sure independent screening, for instance, is a popular method that uses a two-stage approach to identify relevant features. In the first stage, a screening function is applied to each feature to eliminate those with weak correlations with the response variable. In the second stage, a multiple regression model is fitted to the remaining features to determine their significance. Partial correlation is another technique that has gained popularity in feature selection. This method measures the correlation between each feature and the response variable while controlling for the effects of other features. Deep neural networks have also been successfully applied to nonlinear variable selection, where the network's weights are used to identify the most important features. Domain knowledge plays a vital role in enhancing variable selection, as it enables the incorporation of prior knowledge and expertise into the feature selection process. However, feature selection in biomedical data poses significant challenges due to the complexity and high dimensionality of the data. Despite the numerous methods available, further research is needed to address the complexities of high-dimensional data. The development of novel feature selection techniques that can effectively handle high-dimensional data is crucial for advancing our understanding of complex systems. Feature screening for ultra-high-dimensional data is a challenging task, particularly when the underlying distribution is unknown or complex. Traditional model-based methods often rely on specific assumptions about the data, which can lead to inaccurate feature selection. To address this limitation, Zhao et al. 2011 propose a novel, model-free feature screening approach that leverages the empirical distribution of the data. This method calculates a screening statistic for each feature, allowing for the selection of relevant features without relying on any specific model. The authors demonstrate the effectiveness of their approach through extensive simulations and real data examples, showcasing its ability to outperform traditional model-based methods in terms of feature selection accuracy. The key advantage of this method lies in its ability to adapt to complex distributions, making it particularly useful in scenarios where the underlying distribution is unknown or difficult to model. By leveraging the empirical distribution of the data, the method can identify relevant features even in the presence of non-normality, outliers, or other anomalies. Through their simulations, the authors illustrate the robustness of their approach, demonstrating its ability to accurately select relevant features even when the sample size is small or the number of features is extremely large. The real data examples further demonstrate the practical applicability of the method, showcasing its ability to identify meaningful features in complex datasets. Overall, the model-free feature screening approach proposed by Zhao et al. 2011 offers a promising solution for feature selection in ultra-high-dimensional data, particularly in scenarios where traditional model-based methods may struggle.